The Gaussian mixture model, or mixture of Gaussians as it's sometimes called, is not so much a model as it is a probability distribution. So let me first build your intuition for what it is, what distribution it is, by a couple examples. So let's say we just have a simple case of a one-dimensional random variable. And let's draw the PDF. If it were the PDF were a Gaussian, if it were a Gaussian random variable, it would look something like that. But in a mixture of Gaussians, we have several individual Gaussian distributions. Maybe there's a tall one like that. Test my drawing skills here. And then maybe there's like a wide one, something like this. And the probability density function for a mixture of Gaussians, if we have a random variable distributed according to the mixture, is going to be a linear combination of these individual PDFs. In fact, it's going to be a convex combination. So it's going to look something like this. Maybe have a good amount of that guy, and maybe have some of that guy, and then it's got some of this other guy here. So the PDF for the mixture of Gaussians is going to look something like this yellow line here. So that's a one-dimensional example. Let me briefly sketch out a two-dimensional example. So I'll use the same colors. Maybe if we had if the level sets or the contour lines for one Gaussian were like that, and we had another one like this, and of course they keep going, then, and so these are going to eventually intersect, but the contour lines for the mixture, of course, it's going to be a single function rather than two functions, so it might start out looking sort of similar, but then you're going to have to, like on a map, if you have contour lines on a map, then they can't cross because they're each lines of constant elevation. So we have something like this. So if you think about what the contour lines on a map look like, if these were each of these, visualize each of these Gaussians as a mountain, then the contour lines of the topology, or the topography rather, of the land would be the contour lines of the mixture of Gaussians. Okay, so hopefully that gives you a little intuition starting out for what this is. And let's formalize this now. So that's one way to visualize it. Another way, which is nice, is through the generative model. So a generative process for this is the following. We have some random variable z, and z is a vector valued random variable, and it's one of, let's say, actually m things, e1 through em. And here I'm going to use this these lowercase e's for the standard basis. So e1 is one standard basis in Rm. e2 is 0, 1, 0, and so on. So z is a vector. It's one of these vectors. And let's say that z equals ek with probability alpha k. So the alpha k's are some numbers that it's a PMF on this finite set here. And then given z, let's say given that z equals ek, the distribution of x will be normal with mean mu k and covariance ck, where mu1 to mu m are some d-dimensional real-valued vectors, and c1 through cm are d by d positive semi-definite matrices. Or in other words, they're d by d covariance matrices. So to each of these vectors, e, so each value of z, there corresponds a mean and covariance for one of these Gaussians. So this z here, this z is a latent variable. So z is a latent variable in this model. And the way that you can think about this, the generative process gives you a nice sort of way to visualize this, a different way than visualizing the PDF, or it's a little bit different. And it says the following. It says, first, draw z. So let's think about this one maybe here. First, you draw z, and in this case, there were only two, so that it was either the first Gaussian or the second Gaussian. So say we draw, I don't know, 1 first. And then we draw a normally distributed point x from this Gaussian, this pink one underneath. So maybe we get, I don't know, like that point. And then we draw another, maybe we get 2 this time, and we get this point. And then we get 2 again, maybe 1 again, 1, 2, 2, 1, 2, 1, 1. And so you can see that we're going to get something which is distributed in this way. And so that's one way, a different way to sort of visualize this model. So let's write down what the probability density, the density function for this model is. Use a different color. Let's use this orange color here. So first, let's look at the marginal distribution on x. The marginal distribution on x, that's really sort of the thing that we're going to be interested in. In this type of model, this z, well, I called it a latent variable. I mean, technically speaking, it's not necessarily, there's nothing about it here that would show that it's mean that it's a latent variable. But usually, when you use a Gaussian mixture model, you think about this z as being something which you're not really, observing directly, but that is a hidden variable. And so the thing that we're usually interested in is the marginal distribution on x. And so this is the sum over z's of the probability of x given z times the probability of z. And z can take m possible values. So we could write this as a sum as k goes from 1 to m of the probability that z equals ek times the probability of x, the density of x given that z equals ek, and that's a normal. So, well, let me put it this way first. And then let's write what that means. So this is the sum, probability that z equals ek, we said was this alpha k parameter. So this is alpha k times the normal density function evaluated at x with parameter mu k and ck, mean mu k and covariance ck. So this is the density function of a mixture of Gaussians. And it's just what we said earlier, right? These are each, we have m different normal PDFs, different Gaussian PDFs, and these coefficients here are it's a convex combination of these PDFs because these coefficients sum to 1. They're non-negative and sum to 1. So that's sort of these pictures that we were drawing before. And these coefficients here are called, these are called the mixing coefficients sometimes. Sometimes we call those the mixing coefficients. So it's a convex combination of Gaussian PDFs. And now let's write down, so it'll be useful for us. We're going to use this model. We're going to use a mixture of Gaussians to model. You can sort of see how this would be useful for a clustering type of problem. Here, these sort of naturally generate clusters. And a mixture of Gaussians gives a very pleasing probabilistic model for a clustering type of problem. So we're gonna take a look in future videos at how to infer the parameters of this model, how to estimate the parameters using the EM algorithm. So using some data, we're going to use the EM algorithm And the following quantities are going to be useful in that sort of derivation. So, of course, in general, the joint distribution on x and z always tends to be useful. And this is, well, we wrote it here, right? It was just this if z was equal to ek, but we can write this as the product of all k's of ek to the zk. This is the kth element of z, which is going to be 1 if z equals ek and 0 otherwise, times the normal density at x with mean mu k and covariance ck to the zk. So these exponents here, these zk exponents, make whatever factors in this product that don't belong there, just ones when zk equals 0, and they make it just the normal thing when zk equals 1. So this will be a useful formula for us. It might seem a bit strange if you haven't seen this trick of putting these indicator functions, these sort of indicator functions in the exponent, but it turns out that this is a very useful notational trick. So here, just to make it clear, this z is a vector. I think that's clear. z1 to zm. Zm? Wait, is it zm? Yeah. No, d. Z. What is it? Oh, no, yeah, that's right. M, because it picks which of the m components you're going to use. Which of the m densities. Okay, so one other formula which will be useful for us. So let me write down the probability that z equals ek equals, or rather, given x, this conditional probability, we can use Bayes' rule. So let me just write it this way. Probability x given ek, that is the probability that of x given that z equals ek, times the probability of ek, divided by the probability of x. And in the top, we just have the usual thing. This is, this, but we can just go ahead and put in k, since we know it's k, alpha k, the normal density with mean mu k and covariance ck. I mean, I could have put the product here, but since we know that I was writing it sort of for a general z here, and here we know z is equal to ek, so we may as well just put k. And then in the denominator, this is just the marginal distribution on x, which we already, right? That was this thing. The marginal distribution on x was just that. So we can just put that down here. Sum over L from 1 to m of, I'll use L instead of k since I already used k. L from 1 to k of alpha k times the normal density with mean mu L and covariance CL. So this formula will be useful, and just a remark here, this is equal to something which we'll use in the future video, is this is equal to the indicator function, the expectation of the indicator function that z equals ek. Actually, I'm not sure if we're going to use it exactly this way, but it is equal to this, the expected value of the indicator function that z equals ek, given that x equals x. Okay, so this formula is going to be handy here for this conditional probability. So that's a mixture of Gaussians, and if we're going to use this for an application, we get some data and we want to infer the parameters. It turns out that because it's a mixture models often are difficult to infer the parameters for, and so we're going to see how EM can be used to obtain estimates for the parameters. So we'll do that next. Okay, see you then.